Okay, thanks. I'll interrupt Sasha to say happy birthday. It's great to, I guess, have him around at UCLA. Let me see. Right, so this is on the sort of same general theme as Lena's talk. So I think I'll start off with one of the same results that she said, and I guess prove a bit more of it. Then the plan is to apply these methods about specialization and so on to sort of two questions, one about hypersurfaces that she also talked about, and another one about classifying spaces of finite groups. Okay, so this is a theorem that's a little bit hard to attribute. It's essentially an article by Bloch and Srinivas from the early 80s, a sort of great, very short article. But Bloch had been using versions of this argument over many years. Actually, Bloch in his book thanks Cohomological for this argument too. So he says, or anyway, the result I want to talk about is if you have a smooth projective variety over a field, then the following conditions are equivalent. So first is that for every extension field of K, so as in Elena's talk, these are not necessarily just finite extensions. The homomorphism from the Chow group of 0 cycles on X to 0 cycles on X over the bigger field is onto, or surjective. That's one condition you can consider. And so this is just sort of a way of saying, well, that the Chow groups of X, the Chow group of 0 cycles is small and remains, in a sense, small over all extension fields. So for example, as the Chow group of 0 cycles on P1 over any extension field is just Z, so this condition is true for P1 over any field, but for example, if X is an elliptic curve over a field, then the Chow group of 0 cycles fits into an exact sequence with the integers, and the kernel is the group of K points of a elliptic curve. And then, of course, if you enlarge from K to some bigger field, then typically this part of the group will get bigger. So, so in other words, this condition is true for P1, and it's not true for elliptic curves, for example, or curves of higher genus. All right, so the question, though, is can you sort of characterize what varieties have this property? And this theorem gives some reasonably meaningful characterization of which varieties have that property. I mean, one thing you can say at the beginning is that the Chow group of 0 cycles for smooth projective varieties is birationally invariant by Fulton, I guess, and Colliotone and Correa. So this is certainly true for smooth projective rational varieties, but also for some other varieties, and it's interesting to understand what that condition means. Okay, so let's see what I'm going to say. Oh, and I translate this as saying, this is my interpretation of Chow 0 is universally trivial. It's equivalent to the condition that for X, if this condition holds. Elena used this following definition of that property, which also is equivalent, namely that for every extension field of K, the Chow group of 0 cycles, well, the degree homomorphism from 0 cycles on X over this bigger field to the integers is an isomorphism. Okay, so already this is kind of a, I think, interesting equivalence that if the Chow group of 0 cycles on X does not get any bigger when you enlarge the field, then actually the Chow group of 0 cycles on X is just Z, and it remains Z over every extension field. Okay, so the nice thing is that the proof of this theorem is quite elementary, and yeah, so it's nice that we get these equivalences. Anyway, the other condition is the one that she described, that there is a decomposition of the diagonal. That is in the following sense, that you can write the diagonal in the Chow group of n-dimensional cycles on x cross x, where n is the dimension of your variety. In that group, the diagonal is equivalent to a sum of something sort of horizontal and something vertical. So I think of, in my pictures, this is the first copy of x, this is the first copy of x, this is the second copy of x. So x cross, let's see, so you can write this, for some zero cycle little x on x, and some, of course, n-dimensional cycle b on the product, but supported on, say, S cross X for some closed subset S that's not the whole space. So S contained in but not equal to X. Right, so again, this decomposition diagonal says that the diagonal is rationally equivalent to a sum of something horizontal like this. This is X cross little x, plus something vertical, so something is sort of supported on x cross a divisor. In my picture, you can't really see, but B is some cycle supported on this product here. Okay, so the thing is that, I mean, one thing you could say would be that in topology, for real manifolds, say, this condition would essentially always be true, at least maybe in cohomology with coefficients in a field. You can always decompose because you have the Cohn formula in topology, the, say, cohomology of x cross x is basically just the tensor product of cohomology of x times cohomology of x. So that says that you can write any class, such as the diagonal, as the sum of products of classes on this factor times classes on this factor. So this, and here we're saying sort of much less than that. We're not sort of completely decomposing the diagonal into products, but just sort of partly decomposing it. But even that, in algebraic geometry, is a special property. It's equivalent to those special properties up there. It doesn't happen for every variety. For example, it doesn't happen for elliptic curves. Yeah?
So the original condition of a block with multiple reflections goes with tensor with Q?
Well, I mean, the thing is, I don't remember exactly what's in the paper, but the point is, this is an easy argument, and this is basically the argument in this paper. So, yeah, I don't think I guess I don't want to analyze exactly who proved what, but this is sort of the basic argument. Oh, well, let me see. Anyway, yeah, you're right. I think in the article, the point is I just don't remember exactly what they considered. Okay. Okay, so I just wanted to prove that. Okay, so yeah, and Elena did part of this. So let's see. So 2 implies 1 is obvious, and so the next step would be 1 implies 3, which basically Elena did. Let's just say that again. So if condition 1 holds, then, well, you want to apply this to one particular field and one particular zero cycle on X over that extension field. So let me just write this down and then draw some pictures. Is equal to the class of some zero cycle little x on X. So I'm sort of using the scheme theoretic language where you think of a variety over field as being one particular kind of scheme. X over some bigger field is a different scheme. But of course, cycles on here determine cycles on that other scheme by some pullback. So yeah, let me just the way I want to think of that, what I'm saying there is, so if you think about the first projection from x cross x to x, in some sense inside there is the generic point of x. That's the spectrum of the function field of x. This isn't exactly an embedding according to the scheme theoretic definitions, but it's like an embedding. This is an injective map of schemes from there to there. And you can take the fiber product of x cross x, just gives you x over the function field of x. And you can then think about what's the generic fiber of this diagonal mapping, the generic fiber of this diagonal over the generic point of x. And that gives you just one particular closed point, in fact, a k-rational point of this variety. So that's one very natural zero cycle on x over a bigger field, and assumption 1 tells you that that comes from a zero cycle on x, so to speak, over the field that you start with. Okay, so yeah, and then the question is just to translate that into this kind of decomposition. I mean, it's straightforward, but let me just spell out this translation a little bit. So just a sort of remark. We have a bijection between, say, what should I call it, j-dimensional subvarieties of x over this sort of function field. Those are in one-to-one correspondence with n plus j-dimensional subvarieties, n is the dimension of x, of x cross x. So given a subvariety of x cross x, you can take its generic fiber, and that gives you a subvariety here. The dimension sort of goes down by n, just because here you're passing from an n-dimensional variety to a zero-dimensional scheme. Right, so something here gives you something here. On the other hand, it could happen that a subvariety of x cross x has generic fiber, which is just nothing. Namely, if the subvariety is sort of vertical like that, then its generic fiber is just nothing. So the one-to-one correspondence goes if you take only those subvarieties whose projection to the first factor is dense. Okay, so if I only look at those subvarieties, the ones whose projection to x is dense, then those things are in one-to-one correspondence with the subvarieties of this x over this bigger field. Yeah, let's see. I should have studied this first, but let's see. Let's see. Okay, this didn't quite. Yeah, I see. Okay. Thanks. All right. So I have this description of subvarieties of x over this sort of function field, and using that you can get an interpretation of the Chow groups of x over some sort of function field like this. So one way to say it is that it's the direct limit of the Chow groups of like open subsets of x cross x, where the direct limit runs over closed subsets S that are not all of x. Sorry, n plus j here, right? Just because subvarieties here of dimension j can be viewed as n plus j dimensional subvarieties, say on x cross x, but you want to sort of kill some subvarieties on x cross x, namely the ones whose projection to the first copy of x is contained in some closed subset like this. And maybe I should also make the point that this Chow group is just a quotient, maybe, and we have an exact sequence. So Chow group of x cross x maps onto the Chow group of one of these open subsets of x cross x. And the kernel is exactly the Chow group of S cross X. So in other words, this is taking the direct limit of a sequence of abelian groups, and they're all just quotient. I mean, the direct limit over a sequence of surjections. You take all the cycles on X cross X, you kill off the ones in here, then you enlarge S, and you kill off some more. In the direct limit, you get this Chow group. Okay, so, right, so our assumption that, that the diagonal is equal to some little x here translates into some statement on X cross X. I mean, exactly this statement here. So yes, we have that equality in Chow 0 of X cross X translates into an equality in Chow n of X cross X. This is some, yeah. This is equal to this plus some error term, where this error term is vertical in that sense, where okay, so we've shown that 2 implies 1 implies 3. Okay, and then just do the last step, so then show that 3 implies 1. So suppose the 3 holds, so we have this decomposition of the diagonal. How does that tell you something about the Chow group of 0 cycles on X? Well, the idea is you have to use the fact that correspondences act on Chow groups. So let's just see. So we have the diagonal equals this sort of decomposition as above. So what does that tell you about the Chow group of 0 cycles on X, or Chow group cycles of any dimension? So we use the fact that correspondences act on Chow groups. That is to say that there's some pairing we have some natural map from, say, middle dimensional cycles on X cross X times cycles of any dimension on X to cycles of that same dimension on X. I think of this as being the first copy of X, and this as the second copy. Sorry about that, but just to keep the argument straight, I have to keep track of what that is. So this product is given by, like, if you take a cycle and maybe call this alpha, a middle dimensional cycle on X cross X and a cycle of any dimension on X, then let's see, what do? You pull back, you multiply, and then you push forward. So if here is alpha, some cycle, and here is maybe z, some cycle here, I take the pullback of alpha, which is a product cycle like this. So that's pi 1 upper star of alpha. I multiply that by z, and then I push forward by the second projection. I get in Chow I of x again. So geometrically, I take the inverse image of alpha, I intersect it with z, and then I push forward to x, and I get some cycle on x. Okay, so, right, but notice that I need some of the assumptions here for this argument to make any sense. So in order to push forward on Chow groups, I need that this map is proper, so x has to be proper over k. And in order to multiply on Chow groups, x has to be smooth. Or, I mean, if x is smooth, then x times x is also smooth over k. So here this uses that x is smooth and proper over k. Okay, let's see. Okay, I'll never. Yeah, sorry. Okay. So you use the fact that correspondences act on Chow groups in that way So therefore, this equality that we're given, we're assuming this property 3 now, this decomposition of the diagonal, that tells you something about, for example, zero cycles on X. It tells you something about Chow groups of any dimension. But anyway, applying that to zero cycles, you conclude that, so for any zero cycle alpha on X, we have that, so the way that that equality tells you that the way the diagonal acts on this cycle is the same thing as the way the sum of two cycles acts on alpha. But the thing is, these things are easy to analyze if I've got things straight. So let's see. X, X. Here's S. Here's this vertical part B. Here's a little x, zero cycle, and here's that horizontal part, x cross little x. So what can I say about these things? So I think, you're right, I think B lower star of alpha should just be 0 because you can arrange for your zero cycle alpha to be disjoint from this set S. So because by some moving lemma, alpha is rationally equivalent to a zero cycle disjoint from capital S. So yeah, there's a moving lemma for zero cycles that you can move it to be disjoint from any divisor you want on X. And once you do that, then when you pull alpha back and intersect with this cycle B, you just get 0. Right, so you just get this. On the other hand, that is also sort of easy to analyze. What are you doing when you pull back alpha, intersected with this horizontal copy of X, you just sort of get a copy of alpha sitting there. And then when you push forward to capital X, you just get just some multiple of this zero cycle little x. Imagine that it's just a rational point. So what you get is that this is just the degree of alpha times the point little x in Chow 0 of X. Right, so what have we shown? So this is, this is equal to alpha because the diagonal acts as the identity on Chow groups. So we conclude that actually every zero cycle in X is rationally equivalent to just a multiple of this 1 point X. So Chow 0 of X is equal to Z times little x. So I'd like to say actually that this zero cycle X has degree 1. That's also clear from this formula. So also the zero cycle, well, it has to have degree 1 because you have this equality, and you consider what that tells you, what that equality tells you when you take the generic fibers of those cycles over the generic point of the first copy of X. So that tells you that the zero cycle corresponding to the diagonal is equal to the zero cycle corresponding to little x in Chow 0 of X over this function field. And this is a zero cycle degree 1. It's a rational point, in fact. So this equality tells you that little x has degree 1. And so we conclude that actually the degree homomorphism from Chow 0 of X to Z is an isomorphism. Right, so this decomposition actually does tell you directly about the Chow 0, tells you exactly what the Chow group of zero cycles on X is. Now for property 1, I wanted to know that the same conclusion holds over every extension field, but actually that's fine, because if you have a decomposition of the diagonal on X, then you have such a decomposition over every extension field. You just take this equality, pull the cycles back to a bigger field, and you have the same kind of equality. Okay, but we have a decomposition of the diagonal over every field. You have it over K, then you have it over any extension field. So actually, the same argument shows that the degree homomorphism from X over every extension field to Z is iso for all fields E over K. And that's, so thus 3 implies 1, and so we're done. Okay, so that makes sense. Sorry, did you want to?
Why does 1 imply 2?
Why does 1 imply 2? I think it was the other way around. Like, oh, I see. I think I sort of showed that like 3 implies 2, and yeah. Sorry, it was like, yeah, something like that. 2 is the strong one. 2 implies 1, 1 implies 3, and 3 implies 2. Yeah, sorry about that. Yeah. So given 3, I actually proved the stronger property. Yeah. Yeah, I think I did actually prove the circle. Okay. All right, so let me give some example of what you can do with that. I mean, yeah, just to give the broader context, let me recall the sort of application that Bloch and Srinivas did of it. They were thinking about reproving this theorem by Mumford. I won't say exactly the version that Mumford says. Mumford, well, let me just state this. Corollary is that if you have a smooth projective variety over the complex numbers, and suppose that its Chow group of 0 cycles is just Z, then you can say something about the differential forms on this. Namely, it doesn't have any differential forms. The space of holomorphic differential forms on X is 0 in all positive degrees. So in other words, some information about the Hodge structures being special or small implies that the Hodge structure on X is in a way special or small. And in fact, you get a stronger conclusion, or at least what as far as we know now is a stronger conclusion. In fact, let's see, for all positive numbers alpha, the rational cohomology of X is supported on some divisor. In other words, there's some algebraic subvariety of subset of codimension 1, such that any cohomology class restricts to 0 on the complement on X restricts to 0 on the complement of that divisor. So this kind of geometric statement implies that the Hodge structure is special, but in general, the converse is not known. The converse is part of the generalized Hodge conjecture. So it's nice that, given the assumption on Chow gives you actually get this stronger geometric conclusion. So maybe I'll just sort of sketch the proof. Oh, by the way, I mean, so the way that you would typically use this is you sort of contrapositively, because differential forms are easy to compute. So if you take a hypersurface of high degree in projective space, smooth hypersurface of high degree, then it will have some non-zero differential forms if the degree is big enough. And so this tells you that if you look at such a thing over the complex numbers, its Chow group of 0 cycles is not just Z. On the other hand, so the way Mumford stated the theorem is actually, if you have some differential forms of degree at least 2, then actually the Chow group of 0 cycles is what he called infinite dimensional, meaning that it's kind of not just Z, and it's not just Z plus an abelian variety. It's Z plus some other sort of connected group, which we don't really understand, I guess. But anyway, but somehow this is the main point of it, that if the Chow groups are small, then you have this sort of conclusion about cohomology. Right, so the thing is, it's kind of easy from this, maybe I won't go through all the details, but it's easy from this equivalence there. So yeah, I mean, I have to skip a few steps, but basically, so we have to use that for this. So the thing is, basically, I'd like to say that that assumption should imply that there's a decomposition of the diagonal, and that should imply something about the differential forms on X. Right, but in order to apply this theorem, I need to know that the Chow group of 0 cycles on X stays small over all extension fields. And here I'm just assuming something about X over one field, so I need to make at least a few remarks about that. Here it's important that the complex numbers, say, is an algebraically closed field of infinite transcendence degree over the prime field. So this kind of statement is expected to be false if you replaced C by Q bar, for example. So over Q. So because of that fact, when you have a variety over C, it's really defined, it can be defined over some much smaller field, some finally generated subfield of C. over finally generated over Q. So X is really defined over some much smaller field. On the other hand, you should realize that the Chow group of zero cycles, tensor Q, can only get bigger when you increase the base field. That's a sort of easy argument involving transfers, I guess. So also, for all fields, say F inside E, any sort of Chow group of a variety over one field to Chow groups of X over a bigger field, if I tensor with Q anyway, then this is always injective. So the thing is, that means, therefore, that if you start with your variety over F, then it's, for one thing, its Chow group of zero cycles, tensor Q has to be just Q, because when you go all the way up to C, it's just Q. But moreover, even when you go from F to some finally generated extension field of that, Chow zero is still just Q, okay? So, so our assumption, because this is true over C, and C is so big, for every finally generated field E over F, the Chow group of zero cycles on E, tensor Q, is just Q. So basically, so that's, here in this theorem, I assume that something holds for every field, but in the proof, obviously, all I need is this for finally generated fields. So then I'm in a situation where the theorem applies. Again, I sort of need the argument everything tensor Q, but nonetheless, the argument works, tensor Q. And so by the theorem tensor Q, so to speak, X has a decomposition of the diagonal with Q coefficients. So in the Chow groups of X cross X, tensor Q. And then this kind of conclusion is enough to tell you something about the differential forms on X, because correspondences act on, say, ordinary cohomology. So now I'll use that correspondences, say, on a complex variety, act on rational cohomology, or yeah, whatever. They act on lots of different cohomology theories. So, yes. So you just sort of analyze, I think I have to sort of interrupt, not go through this proof completely, but basically you just analyze what this tells you. And that diagonalizes the identity on rational cohomology, whereas these things act in some special way that sort of kills part of the Hodge structure. Yeah, so I think I just have to interrupt and say that leads to the conclusion that this leads to the conclusion that these differential forms are zero for I greater than zero, and even the stronger geometric conclusion. Basically, you find that any cohomology class. Yeah, let me not try to spell it out. Okay. Okay. All right. So this is sort of the way Bloch and Srinivas apply this argument. Okay, so now I wanted to present some sort of more recent applications of that same kind of argument. Okay, so more recent applications. Okay, so one of them was about Chow groups of classifying spaces of groups. Yes, you can define the I codimension I Chow group of the classifying space of a group over some field. Let's say G is, to be specific here, say a finite group, and K is a field. You can define this to be the I codimension Chow group of some open subset of a representation of G divided by G, where U inside V is open, and G invariant. V is a representation of G over the field that we're talking about. Open means Zariski open. G acts freely on this open subset, and you have a quotient variety. And finally, I make the assumption that the codimension of V minus u is rather large, and I is less than the codimension of V minus u inside V. So if I want to define this group for some particular number I just have to find some representation such that G acts freely on that representation outside some high codimension subset, and you can always do that. If you take, for example, V to be take any faithful representation of G, take the direct sum of a lot of copies of that. If you take enough copies, then this condition will be true for any given value of I that you want. So the fact is that this is, which is maybe proved by me and also by Morel and Vygotsky, that this is independent of the choice of representation. Depends only, so it really only depends on the group G and this space field. Okay. So, okay, you can make that definition. And I mean, why do that? I guess, one reason is just that this is about the simplest way to construct varieties that comes to mind so that they have a lot of torsion in their Chow groups. So if you're interested in understanding torsion in Chow groups, then these are sort of model examples, these very special quotient varieties. Okay, so let's see. So a sort of experimental fact was that when I tried to compute these groups, I wrote a book about this recently called Group Cohomology in Algebraic Cycles. So in this book, I tried to compute these Chow groups as systematically as I could for small finite groups G. As with group cohomology, the calculations sort of reduced to the case of P groups. So a fact was that for all the reasonably small P groups, this Chow ring was essentially independent of the base field. A P group of order at most P to the fourth for an odd prime P, or G, a 2 group of order at most 32. It turns out that this Chow ring is independent of the base field, assuming the base field contains enough roots of unity. And the Chow ring of BG over K is independent of K whenever, let's say, K contains the nth roots of unity, and where n is the exponent of G, the greatest common divisor of the elements of G. So, right, and it's sort of mysterious. I mean, just when you can compute this ring, that turns out to be the case. So, I mean, I guess sort of one simple reason why that might happen is if you can sort of analyze this quotient variety by hand, like if you can cut it into pieces that are open subsets of affine spaces or something like that, then that kind of property will be true. Yeah, so somehow you struggle and struggle for all these small P groups, you find that is true. Yeah. I guess maybe there's some hints that there might be some general reason why that could be true that came up in Merkuriev's work. So let's see. So remark is that for any, let's say, finite group, a lot of this works for algebraic groups too, but anyway, and any fields, K, Chow I of BG over K is generated by Chern classes of representations if the number I is, let's say P group G, and any field, Chow I is generated by Chern classes of representations of G if I is at most P. So for a P group in degrees up to P, these things are just generated by Chern classes of representation. So this follows from the Riemann-Roch theorem, the Grothendieck-Riemann-Roch theorem, to relate. So in this range, there's a very good connection between Chow groups and K0, everything in Chow groups is a Chern class of something in K0, plus Mercuriev's theorem, his work on equivariant K-theory, which basically gives you a computation of K0 of the classifying space. It's sort of just the completed representation ring of G, which is analogous to a theorem in topology by Atiyah, I guess. So sort of, it's a little bit weird because that means that if you're interested in K-theory, then BG, these quotient varieties are very simple. All the vector bundles on them are sort of built out of representations of G. And so in this range, all the algebraic cycles on these quotient varieties just come from representations of G. And that explains this fact because, so in that low range, that explains why these groups don't really depend on the base field, because representation theory of G doesn't really depend on the base field as long as you've got enough roots of unity in there. Okay, so that's it. So that sort of explains why this happens in low degrees, but on the other hand, doesn't say what should happen in high degrees. So what I could show recently was that actually things go bad in high degrees. So let's see. There are p groups of order p to the fifth for any odd prime. This is based on other people's examples, so I'll explain in a second. And also there are groups of order 64, 2 to the sixth, G, such that the Chow groups of these quotient varieties genuinely depend on the base field, even when K contains Q bar, let's say. Depends, or one way to say it is, let's say, the Chow groups of BG over Q bar mapping to Chow groups of BG over some bigger field that's not always onto. For some field F containing Q bar. So I should make the point that it's important that I'm talking about arbitrary fields here, not just algebraically closed fields, because Suesselin's rigidity theorem tells you that torsion in Chow groups does not change when you go from one algebraically closed field to a bigger algebraically closed field. And as I should have said, these Chow groups of BG are all torsion, sort of just like the cohomology of a finite group. So this stuff, it's all torsion. And so if I went from Q bar to a bigger algebraically closed field, then nothing would be changing. But if you go from Q bar to some kind of function field, then I'm saying they can change. For these small groups, they don't change. But for bigger groups, they do. They actually can change. Okay, so the question is, why does this happen? Let's see. So the size of these groups may already suggest the answer. So the fact is, the sort of lemma that lies behind this is that if BG has non-zero unramified cohomology, let me not worry about what the coefficients are, then for some positive number I, then I claim that the Chow groups of BG can increase when you enlarge the field. Then there exists a field F containing Q bar, and there exists a number I, maybe a different number J, such that the Chow groups of BG increase when you go from Q bar to this bigger field. So that this homomorphism is not onto. Okay. And then various people, including Kunyavsky in this room, gave examples of these p groups of this size or of order 2 to the sixth, for which there is non-zero unramified cohomology. In those cases, it's always non-zero Brouwer group. So such examples by Saltman, Bogomolov, and many others. Oh, yeah, I'm sorry. That's right. That's right. So this is, so as I say, this is an invariant of the function field. That's what I'm talking about. That's right. What he's saying is that for a non-compact variety, such as these quotient varieties, there are two different things you could mean by unramified cohomology. You want it to be unramified on just the divisors that you can see there, or on all the divisors in some compactification. And here I mean all the divisors in some compactification. Okay, so let's see. So the question then is, I'd just like to say briefly, so why then is why is this lemma true, at least in some sketchy form? And basically, this is also following from the idea of decomposition of the diagonal. There's some messy details because BG is not compact, and I have to sort of think about the difference between open varieties and compact varieties. But basically, it's the same kind of argument. I'll just say a few words about that proof. Let's see. Okay, so the proof of the lemma uses result by Merkuriev that Elena also mentioned, although in fact it's if and only if. So Merkuriev showed that for a variety that's smooth projective over a field, then Chow 0 of x is universally trivial. So in the sense that those three equivalent conditions hold, well, there's yet another equivalent condition that's equivalent to x has trivial unramified cohomology with respect to all cycle modules. Over little k. Cycle modules are these objects defined by Ross. There's some functors from field extensions to graded abelian groups with a lot of extra structure. I won't try to describe them, but in particular, this is it's the most general notion of unramified cohomology. It includes the usual notion of unramified HI, étale cohomology HI. And again, actually, this proof is sort of yet another, well, I mean, in some sense, because it's such a general result, it kind of has to be a sort of universal argument like the ones, it involves, again, thinking about the diagonal on x cross x, this proof. Right, so basically, I mean, maybe I'll just interrupt what I'm saying here. So basically then, if BG has some unramified cohomology, then that tells me that Chow 0, a compactification of x, is not universally trivial. In other words, a compactification of these BGs, or U mod Gs, does not have a decomposition of the diagonal. That isn't quite enough on the face of it precisely because of this issue that I'm interested in Chow groups of these non-compact varieties. And it could be that you could have a compact variety that has pretty big Chow groups, whereas those Chow groups are sort of concentrated on some divisor. But maybe let's just say that getting from there to the lemma is the relatively easy part. So I just, let's see, stop there. Right. Somehow this is the main. Yeah, kind of. I mean, it's just sort of, I mean, I was just saying that you contemplate this decomposition of the diagonal, especially there's the great fact that you can employ that sort of looking two different directions, right? It's sort of, from one angle, it's telling you something about the Chow group of zero cycles. From another angle, it's telling you something about the Chow group of cycles of all different dimensions. I think I just have to leave it at that. Right. But that's sort of, yeah. Okay. I just wanted to conclude with sort of the other recent application, which is what Elena was discussing more, So this one that, so again, theorem that if n is at least 3 and d is some number that's at least twice n plus 2 over 3 rounded up, then a very general hypersurface x in Pn plus 1 over the complex numbers is not, say, retract rational. And hence not stably rational, and hence not rational. So what the main thing that was known in this direction was, known was by Kolar that in essentially the same range of degrees, but actually very slightly higher. So if the degree is at least n plus 2 times n plus 3 over 3, rounded up a tiny bit bigger, then we knew that a very general hypersurface in that range is not rational. Well, actually, so what he showed is that it's not ruled. In other words, it's not birational to P1 times some variety. Hence, it's not rational. Okay. Right. So I might say that sort of, maybe I should make the point that it's quite possible that all smooth hypersurfaces of degree at least 4 in any dimension are not rational. As far as anybody knows, that's probably true. But I mean, this is sort of the best we can do. If the degree is at least n plus 2, then your variety is not Fano. It's not covered by rational curves. It's sort of nowhere near rational. But if you're between degree about 2/3 n and n, then this is interesting. Okay. So, I mean, my proof was sort of building on the arguments by Vozin and Kolyotolin and Pirutka, who proved this for degree 4. Right, but I also had to sort of reuse the same idea that Kolar used in his argument. So Kolar's argument was like this, that you argue that a hypersurface in this range of degrees specializes to a singular variety in characteristic 2 with strange properties. So in this range of degrees, x specializes to a singular, let me just say Fano, a singular Fano variety y in characteristic 2 with sort of properties that you would never have in characteristic 0, with the property that, well, it has a resolution of singularities that you can write down. It has very simple singularities. Sometimes in some dimensions it's nodes, some dimensions it's a little more complicated than nodes, but anyway, very simple singularities. You resolve them and you find that, this resolution having non-zero differential forms on it. H0 of z with coefficients in omega n minus 1 is not 0. So all the varieties that I'm talking about have dimension n here. So this is, z it's a resolution of singularities of a singular Fano variety. It couldn't have any n forms, but it has sort of the next thing. It has some n minus 1 forms. So that could never happen for n is the dimension, this is a hypersurface in Pn plus 1, so x has dimension n. Yeah, so everything has dimension n. Okay. Okay, so, right. Let's see. Oh, yeah, okay, so why could this sort of not happen for something, birational to a Fano variety in characteristic 0? Well, it's because, for one thing, you could just compute these groups in characteristic 0 for hypersurface, and you see that they would be 0 for low degrees. But another way to say it is that if hypersurfaces in characteristic 0, if they're rationally connected, then they have a P1 inside them where the tangent bundle of the P1 of the variety restricted to the P1 is ample. That's called having a very free rational curve, and that sort of implies that this doesn't happen. Yeah, so in other words, a way to describe what's going on here is that y and z are rationally connected, but they're not separately rationally connected. So this is a sort of typical mythology of characteristic P. And Kolar just proved this by sort of computing what this bundle is, finding some line bundle inside there, and seeing that that line bundle is positive enough to have some sections. Sort of just, I'm not saying, by the way, what this specialization is. It's pretty simple. You specialize your hypersurface to a double cover of a hypersurface of lower degree. But anyway. In characteristic 2, you arrange for that to be an inseparable double cover, and then you find that the tangent bundle of that variety you get in characteristic 2 has this rather peculiar property. Okay, so the way so sort of the way Kolar's argument went was using this, or maybe he had to use slightly more than what I've actually written there, but essentially using that plus a bit more. Kolar showed that these varieties in characteristic 2 are not ruled. And then the good point about ruledness is that we know sort of how ruledness behaves in families, in a sense. So then he used Matsusaka's theorem that that sort of ruledness degenerates, or ruledness specializes. Let me not maybe write down that formally, but if you have a family of varieties, let's say over a discrete valuation ring, and if the geometric generic fiber is ruled, then the geometric special fiber is ruled. So that sort of proves that then, you have this family varieties in characteristic 0 specializing to something in characteristic 2, which is not ruled. Therefore, the general varieties in characteristic 0 are not ruled. So that was the way Kolar did this. And then the question then was, how can you determine whether these varieties are actually stably rational? So the problem is that we don't really know how rationality behaves in families. We don't know, say, if you have a family of smooth projective varieties where most of them are rational, we don't know if a limit, if all the varieties in the family are rational. So we don't know the analog of the statement, but using these arguments about Chow groups, that allows you to do some sort of parallel specialization arguments. So nowadays for my argument, use Collier-Toulon and Pirutka's specialization lemma for the Chow group of 0 cycles. So how does that work? So basically that's going to say that in order to show that general hypersurfaces in characteristic 0 are not retract rational, we're going to do that by showing that Chow 0 of these varieties is not universally trivial. By this kind of specialization argument, it's enough to show that these varieties in characteristic 2 have interesting Chow 0. So it's going to suffice for the theorem to prove that that Z, this resolution of this weird variety in characteristic 2, has Chow 0 not universally trivial. Then it'll imply that these varieties in characteristic 0 have Chow 0 not universally trivial. And by the way, that condition about the resolution being Chow 0 nice is fine in this case because the singularities of Y are so mild. Have I got the time right? Yeah, I think I have about 0 minutes. Is that right? Yeah, okay. Okay, so let's see. Right, so basically all I had to do is just sort of imitate that argument by Bloch and Srinivas. Let's see. So the sort of the main lemma that I had to do was this, that so let X be a smooth projective variety over any field. Okay, so then if the Chow group of 0 cycles on X is universally trivial, Let me spell it the other way around. So suppose that you have some differential, non-zero differential forms on X in positive degree. If you have some non-zero differential forms on your variety in positive degree, then Chow 0 of X is not universally trivial. The nice thing being that this is true in characteristic P just as it's true in characteristic 0. Where this was known by Bloch and Srinivas. And in fact, you can kind of spell out what's happening in the two cases, characteristic 2, characteristic P or characteristic 0. So if the field has characteristic 0, then the conclusion you get is that Chow 0 tensor Q is not universally trivial. So in other words, differential forms on a variety in characteristic 0 are telling you about Chow 0 tensor Q, whereas in characteristic P, differential forms are telling you that Chow 0 mod P is not universally trivial. I mean, for the argument, it doesn't matter. I just need to show that Chow 0 is not universally trivial in some sense, but this tells you what's actually going on. So because we're specializing to a weird variety in characteristic P, specializing a Fano variety in characteristic 0 to a variety in differential in characteristic 2 that has some differential forms, that tells you that there's an obstruction to decomposing the diagonal with sort of mod 2 coefficients. And so if you kind of follow through the argument, that means that these hypersurfaces in characteristic 0, I mean, they have the property that Chow 0 of X over C is just Z, but over some bigger function field, Chow 0 acquires some 2 torsion. And therefore, these varieties, even over C, are not like stably rational. So it's sort of, but yeah, I should say that for rationally connected varieties, Chow 0 of the variety over any bigger field is tensor Q is just Q. The only way these varieties, these Chow groups could increase is by acquiring torsion, and that's what is happening. Okay, so stop.